Hello, my name is Mr. Davis and I'm going to be teaching you guys on Monday morning. I've been instructed to teach you guys about black body radiation, Wien's law and the classification of stars. And so I thought I'd make you this video so you could see some of the material before the lesson on Monday, give you an opportunity to kind of get your head round it or maybe do some pre-reading into the topics so that when you come in on Monday morning, you're going to know exactly what we're talking about. I hope you have a good weekend and I'll look forward to meeting you on Monday morning. So I want to start with this photo here. They call this region of space the grand star-forming region. And it's a globular cluster with about 1 billion stars in. And each of these stars are all baby stars. And the baby stars themselves are formed from the gas clouds that surround them. The reason I love this photo is because of this little fella up here. All the stars look quite the same, apart from this little star over here, which is a different colour. In science, when we spot something like this, it often means that it's worth investigating. And when scientists did investigate, they discovered that there were actually a huge variety of different coloured stars out there. As you can see by this photo taken by the Hubble telescope, there are a variety of different stars out there, all different colours. It's clear to see that there are some reds, blues, yellows, even some oranges out there. And with this many available, classification is absolutely necessary. As scientists started investigating stars in further detail, it became clear that the colour of a star was an indicator of the temperature of that star. So red stars tended to be quite cold comparatively, at about 3000 Kelvin. And as you went up through the scale, you saw red to orange to yellow to white to blue to purple, purple being the hottest of all the stars at about 50,000 Kelvin. To a good approximation, stars can be thought of as black body radiators. This is a theoretical body that absorbs all the radiation that falls on it. As well as that, these black body radiators also emit all wavelengths of light, but has a maximum wavelength intensity. This maximum wavelength intensity is the colour of the star that we actually see. This graph is the examinable section from the AQA astrophysics module, and it demonstrates what I mean by maximum wavelength intensity. Imagine you look up in the night sky and see an orangey kind of red star. The temperature of that star would be 4,500 Kelvin. The radiation that star is producing is far greater than the orangey red that you're seeing. In fact, that star is generating radiation across the entire spectrum, including gamma rays, UV, infrared, and radio waves. It just so happens that the maximum wavelength intensity is here, so what we actually see is a red-orange star. The same can be said for a star which would be yellowy, kind of whitey colour with a little tinge of green. This star would be at 6,000 Kelvin. It's generating all different types of wavelengths, but the maximum wavelength intensity here is at this point in the spectrum, so the star we see is yellowy, whitey, greeny colour. And finally is this large peak here. The star would be a purple colour. That's because the maximum wavelength intensity is here, but it's still generating all these wavelengths. We just can't see them because this is the most intense maximum wavelength that we're looking at. Now, although you can't get a perfect classification system, we attempted to classify them based on the most predominant wavelengths that we could see, or the most intense wavelengths we could see from a variety of different stars. And this is the spectral classes that were invented. So you've got class O, B, A, F, G, K, and M. Class O being at the hottest end of the spectrum, and class M being at the coldest range of the spectrum. Our own sun is a class G star, and its temperature falls sort of between 5,000 to 6,000 Kelvin or so. So the final thing I need to discuss with you is Wien's law. Wien's law is a way of determining what the maximum wavelength intensity would be based on the temperature. Wayne's law says that the maximum wavelength intensity can be found using this simple equation here. The maximum wavelength intensity times by the temperature is equal to a constant, and that constant is 2.898 times 10 to the minus 3 meter Kelvin. That equation is found on the datasheet and can help you determine what the temperature of a star is based on its maximum wavelength. And finally, I hope you understood everything on the video. If there was anything that you were unsure about, you can re-watch this video, or you can grab a textbook and just look it up so that when you come in on Monday, you're comfortable about what we're going to be covering. My final request is also that you prepare 6 keywords from this video topic that we've looked at. If you could bring them to the session, make a note of them somewhere, that would be great because we're going to be using them. I hope you have a great weekend, and I do look forward to meeting you on Monday. Thanks, bye.